In this lesson, we're going to look at evaluating logarithms, and when we evaluate logs or find what logs are equal to, all we're really using them for is to solve for exponents. So for instance, we would know that 2 squared equals 4, and we know that 2 cubed, 2 times 2 times 2 equals 8. But if we were asked to solve for an exponent, so say 2 to what power is 4, or 2 to what power is 8, we would know that it was 2 and 3. But if it asks the equation 2 to the power of x equals 6, we wouldn't know that value because there's not a whole number that we could raise 2 to the power of and get that value of 6. So that's what logs are for, and we'll get more in depth into this, but for right now, if you guys did 2 to the power of 2.585, it should get you at least close to that value of 6. So logarithms are used to evaluate or solve for exponents essentially. So mathematics define this x value using a logarithm, and we would write log base 2 of x equals 2.585. And instead of writing x, we would write in place here log base 2 of 6. So 2 to the power of 2.585 would equal 6. So the definition of a logarithm with base b, it says let b and y be positive numbers, b can't be 1. The logarithm of y with base of b is denoted or written as log base b of y equals 6 if and only if b to the power of x equals y. So right here, guys, is how we are going to rewrite or go back and forth from log form to exponential form. So what happens is the base of your log comes over and becomes the base for your exponent, and you're left with what is left over there on the right. So it might not make much sense right now, but that little note there is going to be key in figuring out how to go back and forth from exponential form to log form. So if we just sort of practice rewriting some of these for right now, it says rewrite the equation in exponential form. So we're going to go from log form, which is what it's in right now, because I can see the word log there, to exponential form. So what happens is we bring the base of that log, this is a log base 3 of 81, bring it over, and it becomes the base for your exponent. Whatever was on that right is now the exponent. That is the inverse, or how we undo logs, and we're left on that left-hand side with just 81. So is 3 to the 4th power 81 3 times 3 times 3 times 3? Yes. So the base of your log comes over, becomes the base for your exponent. So if we look at number 2, log base 6 of 1, the 6 comes over, 6 to the power of 0 equals 1. Anything to the 0 power is 1. Log base 14 of 14 equals 1. That base comes over, becomes the base for your exponent of 1. That's gone. 14 is left. Is 14 to the 1st power 14? Yes. Now, when you guys have fractions, log base 1/2 of 4 equals -2. Whenever you're going from a fraction to a whole number or vice versa, the only way to get from a fraction to a whole number or a whole number to a fraction is with a negative exponent. So let's just write this out and then look at it and see if it makes sense. So this becomes 1/2 to the negative second power, log's gone, equals 4 on the left. So if we use our exponent rules and distribute that negative 2 in there, we would get 1 to the negative second over 2 to the negative second. I'm going to flip both of those to make them positive exponents. So what happens is you get 2 squared over 1 squared, which is 4 over 1, and that is 4. So anytime we're going from a fraction to a whole number or whole number to a fraction, you have to have it equal to a negative value. And we will look at a couple more of them, but just sort of keep that in mind. So we're going to look at those 2 little key boxes down there at the bottom, and then we'll do some examples together with practicing. But down at the bottom, we've got this box with the logarithm of 1 and logarithm of base b with b. So if you guys are looking at logarithm of 1 or logarithm base b with b, it just says that log base b of 1 equals 0 because anything to the 0 power is always 1. Then it says logarithm of base b with b is always equal to 1 because anything to the first power is always itself. So these are sort of examples. Logarithm of 1 is what we had here, and logarithm of base b with b is what we had there. Log base 14 of 14. It's when the base and the argument, the small number and the big number, are the same. It's going to equal 1. Whenever you have a base of any value to the argument of 1, or the large number is 1, it will always equal 0. So then the other thing we have to discuss is the common logarithm and natural logarithm. So just like if you guys don't see a power, say you had y squared times x. Even though you don't see it, you know that that exponent is a power of 1. Just like in our radicals, if it's a cube root, it would say cube root. But if there's no index there, you guys know it is a square root, an index of 2. Same goes for your bases. We work in place values of 10. And so if you see a log like this one here, that's just log x, you guys have to know that it is a base 10. So if you don't see a base, you need to know it's a base 10. One of those sort of unwritten rules that you guys just have to try and remember. Any other base, it will say log base 3, log base 7, log base 1/2, log base 1/3, log base 7. It will say it if it's not a base 10. If there's nothing there, it's base 10. So the other logarithm we have is just the natural logarithm. So your natural logarithm is that log base e, or that e value that we were discussing. So what happens is the e and the ln are just inverses of one another. And we'll talk more about that when we find inverses. But they essentially undo each other. So log base e or natural log are the same thing. Log base e of x or natural log x, they're both the same thing. So we'll practice some to get you a little more familiar with them.